Hey, so today we're going to prove that the negation of P or Q is logically equivalent to the negation of P and in the negation of Q. And we're also going to prove that the negation of P and Q is logically equivalent to the negation of P or the negation of Q. Okay? These are known as De Morgan's laws, these two guys. Okay? So we have the truth values. We want to have all the possible truth values between P and Q. So we can get that by doing true, true, false, false, true, false, true, false, right? Okay, so the negation of P is just the opposite of what P is here. So this will be false, uh, false, true, true. The negation of Q is the opposite of Q here. So this will be false, true, false, true. And now we're going to have the negation of P and the negation of Q. So we're going to look at these two columns here. So this will be F and F. Remember for and, both the negation of P and the negation of Q must be true in order for this whole proposition to be true. So false and false is false. False and true is false. True and false is false. And true is true. Okay? So now we're going to do the negation of P or the negation of Q. So remember with or, all you need is at least one of these propositions to be true in order for this entire proposition to be true, or these components, the components to be true for the entire proposition to be true. So we have false or false will be false. False or true is true. True or false is true. And true or true is true. Notice I use not P, the not P and the not Q column in order to construct the not P or not Q column. Now we're going to do, so now we have not P and not Q, right? And we have not P or not Q, so we're about halfway done. Now we got to get this not P or Q and this not P and Q. So first we got to do P and Q and P or Q, and then apply the not function onto it, right? Okay, so we're going to have, let's see, what can we do here? So P and Q, so we're going to look at these two columns here. So true and true is true. True and false is false. False and true is false. False and false is false. Okay, so now we're going to do P or Q. Remember for P or Q, both components, at least one of the components needs to be true in order for this whole proposition to be true. So we have true or true is true. True or false is true. False or true is true. False or false is false. So remember for the and here, we needed both of these to be true in order for this whole proposition to be true, both P and Q. Okay, so now we're going to apply the negation of P and Q. So we're going to look at P and Q and do the opposite. So this will be false, true, true, true. And we're going to apply the opposite of P or Q. So this will be false, 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 true. So notice we have for neg P and neg Q, we have false, 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 true. And for neg P or Q, we have false, 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 true. So notice these produce the same truth table. So this implies that the negation of P or Q is logically equivalent to the negation of P and the negation of Q. And look what we have here. We have the negation of P or the negation of Q is false, true, true, true. And for the negation of P and Q, it's false, true, true, true. So that means that the negation of P and Q is logically equivalent to the negation of P or the negation of Q. And that is what we set out to do, right? So notice this guy is logically equivalent to this guy by truth table. And this guy, right, column 2 that I'm going to name, is logically equivalent to this neg P and Q over here, right? And that's how you can show that these propositions here are logically equivalent to each other.